Hello, my name is Gabe Van Solkema. I'm a senior developer at Configura. I've been with Configura for almost 9 years now. Spent the first half of my time developing commercial interior extensions, custom extensions for manufacturers, and I've spent the second half of my time doing the exact same thing on the material handling side of things, developing custom MH extensions for manufacturers, integrators, etc. But throughout my time, have had a few chances to work with the product team, which is our internal team here at Configura that is in charge of developing core functionality, abstract functionality, and our generic extensions like Fika Office, or if you're on the MH side of things, the MH Essentials. Fika Office especially is relevant to our conversation today. That conversation being electrical system fundamentals. Learn how to program an electrical system leveraging the new pathing abstract and being able to reference the example implementation that we have created in Fika Office. Let's get started. Okay, I want to start by giving an overview of the topics that we will be covering today. That way you have an idea as to where we're starting and where we're headed. And to begin, I do want to get this out of the way. What I believe to be a simple truth, and that is that electrical systems are complicated. Oftentimes, in my experience, they are the most complicated thing in a custom extension, that custom electrical system. Every single one has unique complexity. They all have different product rules, requirements, etc. Ultimately, I think they are fun to develop once you get into the swing of things and if given enough time to actually develop a robust solution. But they can also be really overwhelming. So, one thing that we internally realized over the past few years, painfully realized, was that we don't really have a great example for electrical systems. We don't have much abstract support for it, if at all, and we don't have anything in Fika Office. So we embarked on this mission to develop an electrical system in Fika Office. And in tandem with that, we wanted to develop an abstract layer of code that could provide a launchpad for any other custom electrical system. Myself and about 10 other developers were part of writing this solution. Between us, we've written many electrical systems, and I will say it was very interesting hearing different people's perspectives on how to architect an electrical system, and then factoring in the fact that we needed to create an abstract layer of code that was simple yet extensible. This is not easy, of course, because you don't want to assume too much, but you also don't want to assume too little. And so finding the right balance was something that we had to iteratively solve for. And collectively, I think we landed in a really solid spot, taking advantage of some of the newer things that we have at our disposal while making sure that the code is clean yet extensible. So to start, we'll be looking at the pathing abstract. This is the layer of code that you will extend from when you implement your own electrical system. Keep in mind that that could be a new system or you may be looking to convert an old system. So first and foremost, we'll look at the A-star pathing algorithm. The pathing algorithm, the underlying pathing algorithm, is sort of foundational to any electrical system. And we've gone ahead and provided the A-star pathing algorithm for you to use out of the box. This is a node-based algorithm, so we have pathing node base classes that you can leverage. And I should note that you can substitute your own algorithm if you don't want to use the provided A-star algorithm. It just has to be a node-based algorithm. So given that we are finding the path between nodes, we do have to be able to store state for created paths. So the pathing node snappers and path snapper classes are available to you for you to use, and these are foundational for how the pathing abstract works. We'll also be looking at animations and vessels, the combination of the two and how those work. And really, animations and vessels are designed to facilitate the UX, right? They're there to make sure that the user can interact with the electrical system, add paths, remove paths, etc. And so they're a crucial component to what we're doing, but they're also not necessarily foundational. Next, we'll look at manual versus automatic routing. Manual routing is the simpler of the two. And at CETX, I had a lot of questions about automatic routing because it's a more robust or powerful solution, and it also provides a better user experience. So it's something that I'm assuming many of you will be looking to develop. And we'll be looking at how Fika does some automatic routing in a generic sense, that is. And really the difference between the two, manual routing is when you have simple node A to node B connections or paths that can be formed. And then automatic routing is the idea that you can click on node A and then click on node C, and two paths are formed with less clicks. So the automatic splitting and merging of paths. And in our case, Fika Office, that would be jumpers. So we'll be looking at how Fika Office implements the pathing abstract, and hopefully you can extrapolate that into your own electrical system that you implement or that you convert. We do have some dummy product rules built in as sort of like an example of how you could implement your own product rules. I know that every electrical system has its own complexity, its own nuance, its own unique product rules, specifications, etc. And so I think it's important that we have some rules in the Fika Office extension, hoping to have more in the future. But as with any electrical system, at some point you have to decide how you are going to behave. And so Fika has made some decisions. And hopefully you can see how those are implemented and use Fika as an example for your own solution. The A-star algorithm. So I mentioned that this is foundational to our solution. The A-star algorithm is a node-based algorithm, and it can be substituted out for another node-based algorithm if you prefer another one, but this is the one that we've provided. So it's widely used in robotics and video games as a pathfinding algorithm, and it's used to find the shortest path between two nodes. So like I said, it's a node-based algorithm. So in order for nodes to path between each other, nodes must know about their neighboring nodes. So if I am node A and I don't have any neighbors, I will never be able to find my way to node B or C or D. Nodes have to know about their neighbors, and this is foundational to the pathfinding logic. So nodes are assigned dynamic scores based on how far they are away from their neighbors and how far they are from the start of the path that's being created and the goal or the end of the path. And those scores are used to calculate the path of least resistance or the shortest path between the start and the goal nodes. So I've been playing some Fire Emblem lately, um, the old Game Boy Advance Fire Emblem games, and it struck me that Fire Emblem is a perfect example of an A-star pathing algorithm because of the tile-based or node-based underlying logic that drives the pathing. And you can see here, this character has an array of blue paths that it can take or blue nodes that it can path to. And currently it's moving off to the left, but if you were to choose another node, it would draw a blue arrow specifically designed to go the path of least resistance or the shortest distance between where you are now and where you're headed. And so this being kind of a visual example in a video game of a node-based pathfinding system, I also have this sort of GIF here for how the pathfinding algorithm actually works. And you can see that there's scores, and then it's trying to find its way from point A to point B. And as it traverses out and up, it eventually finds its way around the black obstacle there and makes its way to B using that path of least resistance, that blue path at the very end. So what do we need in order to develop our own pathfinding system? First and foremost, we need pathing nodes. And these nodes need to be generated by things that are in the drawing. We don't have a tile-based coordinate system, but we do have space positions that we can use. And so each pathing node must provide a position in space coordinates, and it has to know about its node neighbors. And so that position in space coordinates is really what we can leverage to figure out how far we are from our neighbors, because they also have space coordinates. And so we're not in a 2D grid, right? We're in a 3D space. So those positions are what we can use to measure or calculate the path of least resistance. So pathing nodes are created by an owner and they cache that owner. When they need to figure out what their neighbors are, they ask the owner, what are my neighbors? This allows for nodes to be dynamically generated and dynamically asked for their neighbors. That leads into my next point. The nodes are dynamically generated. So if the first node is the start node, it's going to ask for its neighbors. And when it does so, nodes will be dynamically generated and sort of the algorithm will fan out by asking from the start about its neighbors, which asks about its neighbors and its neighbors. And those nodes are dynamically generated or provided by their owners, which are the objects in the drawing. We also have pathing node snappers. So these are specific snappers that are designed to generate start and end pathing nodes. So these are the snappers that animations will directly work with to allow for users to click on a start node and then click on an end node to create a path. So for paths that have been created, we have path snappers. And these are connected to the start and end pathing node snappers that the user clicked on. And then in order to connect the pathing node snappers with path snappers, we use a multi-link connector, which allows for many-to-one relationships or connections. So one node could be connected to multiple paths. And of course, each path is going to be, it's going to need to be connected to its start and its end node. And the multi-link connector doesn't necessarily care about positions or rotations. It just allows for snappers to reference each other. We're going to have some animations that work with the pathing node snappers and path snappers to facilitate creating and removing paths. At the end of the day, that's what we're trying to give the user the ability to do, is create paths or create junction cables, sorry, jumper cables, and then have the ability, of course, to remove the paths that they've created and customize their system. And then, of course, we need our path snappers or our jumpers to update dynamically as snappers are moved, stretched, disconnected, etc. So paths that have been created have to respond to updates to the system. So for example, if we have a panel run of Fika panels, if we were to disconnect the run, if we were to disconnect one panel from another and break the path, we would want the jumper to be removed as well because it's no longer valid. Or if we were to shorten the path or lengthen the path, we would want the jumper to react and get larger or smaller, or potentially remove itself if it's no longer valid. So the dynamic updating of paths or jumpers that have been created. So before we really dive into the code or we get really technical with all the nuance, I want to demo the Fika electrical system that's been implemented by our team, and hopefully that will give you sort of like a visual context for some of the concepts that we talk about. And when we do that technical deep dive, some of the specific code that we look at. Um, so to start, I'm going to actually navigate to the electrical view mode. This is a new view mode that was added for this system. And the first thing you'll notice are these gray spheres that are showing up at the bottom of panels and junctions. These spheres are our pathing nodes, or at least the graphical representation of them. Just like when we were looking at the Fire Emblem graphic earlier, where there was a tile-based 2D system, um, we have nodes. They just exist in this 3D space. And they each, as you can see, have a position and maybe what isn't so apparent, but graphically it makes sense. Uh, each node has an owner. So this node on the end is owned by its junction. This one in the middle of this panel here, this panel raceway, is owned by the panel, and so forth. So each node is provided by its owner. I think that that's the key word. These nodes are dynamically provided. So currently, none of these nodes actually exist. Um, but they will when the pathing algorithm is ran. And these are exactly where the nodes will generate, and these nodes will be used to facilitate pathing. So each node that gets generated dynamically can ask its owner for node neighbors. So this node can ask the junction snapper for node neighbors. And so the junction snapper, within the context of this panel system, can ask its panels or its adjacent panels that it's connected to for nodes that might be considered a neighbor. And so in that way, the junctions node um, can know about the panels node and have that node be its neighbor, and so forth. So this panel node can be neighbors of both the junction node to its left and the junction node to its right. Okay, before we create a path, we need to add a power module. So you'll notice that all the animations are in this toolbox section in the Fika Office library, and they are currently hidden behind a develop mode flag. I'm going to go ahead and start this animation. What this allows for me to do is to add power modules to my panels, and the power modules are what the panels require in order for them to facilitate pathing. So I'll go ahead and add one. Um, and you'll notice now I've got this gray brick here. And so I'm going to start the pathing animation. And you'll notice that there are now two green nodes that can be targeted. So I've started the create jumper animation designed to allow for the user to create a new jumper. And the power module that I added earlier, when I added that power module, I actually added two different nodes, one on either end of the power module. These nodes are a little different than the gray nodes that you see here. So these gray nodes are dynamically provided and they facilitate pathing. They have neighbors, right? But we can't click on these nodes to start or end a path. They can't be the start or the goal node. They are just intermediate nodes that can help us get to our destination, but cannot be the destination. Um, and I mentioned earlier that there's a specific pathing node snapper designed to connect to a path snapper. This is that snapper. So there's two of them right now, one on either side. And these snappers are actually children of the panel. So this is a child snapper of the panel, and this is also a child snapper of the panel. And these child snappers were added when we added a power module. Now, when I actually click, what's going to happen is it's going to broadcast out to the other pathing node snappers that I have been clicked. And it's going to see if those snappers can be a valid destination. So if my first click is the start of my path, my second click would be the destination. And now here's our first example of a product rule where I can't click on the node on the other side of the power module because that doesn't make sense. They're already linked together via this electrical box. Um, and same if I were to click on this side, right? There's nothing for me to click on over here, and I can't route to the the node on the other side of my power module. So without another power module, I can't really create any paths. So I need to add a power module to one of my other panels. So I'll go ahead and do that. And then let's start our pathing animation again. And I'll start by clicking on this one. So you'll notice now that this node over here is green and it can be pathed to. So this is a valid path that can be created. And how it was able to determine this, I'll try and explain. And I think this is critical to your understanding of how the system works. So when I click on this node, it traverses out into different directions and it figures out what it can or can't connect with. So this node is a potential destination. And when I click on the node on the other side, it deems that this is not a valid destination. And because it's part of the same power module, we actually just hide it altogether. But we are able to traverse down these intermediate nodes over to this power module node here. So this is a valid path. So if we were to click, we would actually create a path snapper or a jumper snapper in between and connected to the start and the end nodes. You'll notice that this one is red, and that's just to say, very clearly state that, hey, there could potentially have been a connection to this, but the connection was invalid. So similar to not having a node on this side over here. But I'll go ahead and click, and you'll notice that now we have created a jumper snapper. We've created a path. This jumper snapper has a multi-link connector that allows for it to connect to the node on its right side and the node on its left side. And these nodes are also connected to the jumper. So snapper child node on left, child of this panel is connected to the jumper snapper, and snapper power module node here, a child of this panel, is also attached to or connected to the same jumper snapper. So in this way, we now have state. We have two nodes connected to one path snapper. I can remove this path with the third animation over here. When I target the jumper, you'll notice that both the start and the end nodes have an arrow above them to indicate exactly where this starts and ends. The path itself is highlighted red, and so as I target it and then click on it, the path will be removed. Let's go ahead and re-add that path, and then let's say there is a disconnect. So this is a valid path. Everything's great. Maybe actually we'll stretch it out a bit. You'll notice that the path recalculates. Maybe make this a little shorter. Again, the path recalculates from the start to the end node. But say I were to disconnect this panel, you'll notice now that the path no longer exists. If I undo this change, the path comes back. So this is sort of what I was mentioning earlier about having a system that's dynamic. Consider a situation like this, where we have three power modules now. And this is where we sort of get into the concept of automatic routing. So if I were to click on this node, you'll notice that I can both path to the power module directly to its right, but then I can also path to this power module that's two panels over. And so really what's happening here, the way that the system is designed to work, I'm going to go ahead and create the path and then I'll explain it. So we started here and we ended up over here. This is a valid path, but a few things took place right about here. So when it got to this node has determined itself to be a split node. What that means is it's forcing a split. It's a bool value on the node. When it was created, it was assigned the value of true, and I should split a path. So if a path gets to me, I can be the end of a path, but then I should start a new path. Additionally, this node had the same rule, right? But it also said, do not create a path between the two of us. And the way it did that is it designated itself as free. So as it traverses across, it starts with the first snapper node here, and it finds this intermediate node. This intermediate node finds this snapper node, which causes the path to end. But we're still trying to path to this node over here, and we think we can make it. So we've identified that this node is in fact a neighbor, this power module snapper node to the right, but it's free, and it should also split its path. And so we'll hop over to there, and we'll start a new path as if it had been split from this specific position. And so from there, we're able to find our junction neighbor node and then again the power module destination. What makes this interesting is when we remove this power module. If we were to remove this power module, we could do a few different things. We could automatically recalculate the combination of the two paths, but in our case, in Fika's case, we've decided to remove the associated paths. So you'll notice that the power module has been removed because it was facilitating both the jumpers to its left and to its right, both of those paths. When it was removed, both of those paths, those jumpers were also removed. And then again, we want it to work with undo. So I just did a Control Z command and our power module and both the path snappers are back. Just to showcase that there are actually two separate paths, you'll see that we can remove each individually. Another interesting thing that happens as a result of how we programmed this system to work specifically for Fika, right? So the product rules that we decided to implement. if you were to create sort of like a looping panel system like this, and you were to click on this node here, you can actually click on this node and it'll route all the way around. And it'll create separate paths for each section. So I think it makes sense to dive into some code and show you how exactly this system works under the hood. And like I mentioned earlier, I want to start with the pathing abstract. And these are the files that currently exist in this abstract. So first and foremost, we have a Pathfinder class. Um, this is designed to be subclassed so that you can provide your own, maybe we should say node-based pathing algorithm. Um, there are some helpful path inventory and path nodes um, calculations that are going to happen on creation. But aside from that, your job is to tell it how to create a new path. And it will use start and goal nodes to create a path. Before we dive into nodes or paths, I do want to show you the A star Pathfinder. If I can navigate to it. Okay. And this friend is our implementation of the Pathfinder class, the A star Pathfinder. And specifically, it calls this A star class. It passes in the start and the goal, and then any nodes that are free. And then, of course, it calls this method getPath. So I'll pull up the A star class real quick here. And again, I'm going to move kind of fast. Hopefully some of these comments here you find helpful. Again, there are costs associated with each node, and its goal is to find the shortest distance from the start to the goal. There are a few different sequences of nodes or sets of nodes that are maintained as the algorithm is ran. So nodes already evaluated, nodes yet to be evaluated, previous nodes, visited nodes, etc. These are for optimization purposes. The real meat and potatoes of the algorithm is in this getPath method. Um, and I think the most important thing for you to see is that it's designed to work with these A star nodes. And specifically, it's going to ask for neighbors. So get neighbors. Um, and that's kind of the crux of the entire system. Uh, a node-based system is nothing without node neighbors. So the idea here is that we're getting our neighbors for the current node, and we're looping through our nodes, resetting current on each iteration of the loop and trying to find neighbors. And it's going to choose, right, the cheapest node, the node with the lowest F score on each iteration. And then it's going to fan out, grab neighbors, and continue to try and find that cheapest node or that cheapest path to get to the end goal. Where you'll see here, this little section, if we found our goal and we can get our path, we go ahead and return it. Return internal get path. Um, this is where we're handling some automated routing functionality where you have the ability to override the cost. So that's why our power modules that were our power module nodes that were to the left and right are directly adjacent to the same power module. Those two nodes that belong to that same power module, their cost when they find each other is zero because um, there is no jumper or cabling required to connect those two. They are already connected, even though there's space between them, right? That space is filled by the power module. If we haven't supplied a cost override, the default behavior is to simply look at the distance to the next node. So that is going to be calculated, and that G new is one of the scores used to uh, calculate the path of least resistance. So the distance here in 3D coordinates is the crucial score that is used to determine how costly it is to traverse from one node to the next, unless you were to supply your own cost override, which is what we do. We zero out the cost in certain cases, making certain nodes free. Um, and again, those nodes are dynamically retrieved. Always, those pathing nodes are provided by their owners. So either child snappers or panels or junctions in our case. So if nodes are provided to the algorithm, we should take a look at those nodes. I'm going to go to the base class here. This is our pathing node base class. And it is identified using its owner and position. The position is in space coordinates. So these two things in tandem are enough to identify any node. Every node is provided by an owner, and it has reference to that owner. And every node has a position in space coordinates. You would never want to have two nodes at the exact same location with the exact same owner. At that point, that is one node facilitating potentially multiple paths. So this is enough. These two fields are enough to identify and cache unique state. Um, this key field is also here though, and it is valuable, I think, because it allows for you to quickly and generically ask the a node for an identifier without having to do casting and then asking an owner a question and then checking to see if there's a specific position that matches. No, you can just simply ask for the key and have keys set up and ready to be leveraged within the scope of your system. So Fika uses this key field to help identify nodes as they're being passed around. This split bool is um, identifies whether or not a node should force a path to split. So we noticed earlier when we created the paths that traversed across multiple power modules, those paths were splitting up and multiple paths were being created. That's because some of those nodes were designed specifically to split paths. And some of those nodes also had that cost override that I mentioned, where they were zeroed out. A -1 cost override is going to, anything less than 0 is going to default to just doing the space calculation. How far am I in space away from my next node? But if you want to be able to override the cost, you just do so here. And then as a path is determined, as the path is optimized, um, this will be assigned the previous node, and it works backwards from the goal to the start. So all 6 of these, or 5 of these, I should say, are passed in as parameters on construction, and then this one is assigned dynamically by the algorithm. And this should be a node. Yes, so this is the generic pathing node class. You can see that you have the ability to subclass different things. And I should say that the identity check has actually been overridden. So the equals operator calls this method here that actually is specifically checking owners, positions, and then also keys. This was an additional check that was added to allow for a key-based system. The owner, if it is a snapper ref, is going to be stored a little bit differently so that we aren't caching references to snappers. But otherwise, it's expecting your owner to be a prop ouch of some sort. And the reason being, these nodes ask for their neighbors, and they ask the owner for their neighbors. Um, and we'll get into this in a second. I do want to just run over how the A star node here has overridden the class and provided the scores that the A star algorithm is expecting to work with, and then some reset and defined path functionality specific to A star. But let's talk about this get node neighbors. So how does this work? We've got our prop obj O, which is our owner, that gets passed in. And then we have the node. Okay, so we have a node and we have its owner, right? This and its owner. So how do we get our neighbors? Um, and this was a design decision we made. We went back and forth on how to facilitate this. But what we decided to do is to take advantage of the prop obj system. So what the prop obj system allows us to do is make a get call. And we are going to pass in the specific prop key, and we're going to pass in the node. So in this case, if we're to ask a certain pathing node, right, for its neighbors, it's going to pass in itself and its own owner and basically say, hey, I am me. I'm passing myself in. Owner, give me my neighbors. You know I'm asking about myself. Um, and the return or the response would be a set of pathing nodes, potentially zero, potentially, you know, however many neighbors that that node has. And so I'm going to go to the panel junction snapper to show you hopefully a relatively simple implementation of this. So if I go to props, you'll notice that we have this stir prop key here that matches the same get call we make. And we're not storing any state. We're not overriding put or giving it a default value, but we do override get. And so when we call get on our prop obj, right? And let's say, for example, this is the node that is generated by the junction snapper. So the junction snapper is going to be asked to get this prop key. And if it chooses to respond like it has, it can do what it needs to do. And in this case, we're going to make sure we have our pathing node passed in as the env, right? The node is passed in as the env, which is that second argument after the key. So we'll cast that, verify that it's a pathing node and not just some other object. And then we can call a method. So in our case, we're going to call a method on ourself, passing in this node. And so by providing our own get specific to this prop key, having get node neighbors PK, we actually are able to also pass in this node as the env and pass this along to a method on our junction snapper. So our junction snapper receives that get and it passes along that answer or that logic to this method. And now here really, we have our node, the node in question, and we need to figure out its neighbors and provide them. And so this is where the keys are really helpful. Because we have keys, we don't have to ask this node for its owner and do a bunch of other stuff. We can just say, hey, if you're a node that has one of these keys, I know that I can route to you. And so I'll provide my node. And you'll see this is where our junction snapper dynamically generates and provides a node. the node being or having an owner that is this junction. And then we have our position that we give it, our space position to space, um, and then our key. So we say, hey, you are owned by me. Here's your position, and here's your key. And so this node would be added to the pathing node set and would be one of the nodes that was returned by this get node neighbors call. Keep in mind, this goes all the way back to the A-star algorithm where we're calculating our get path, and get neighbors is called on current. Get neighbors is called on this node. This node is going to ask its owner. Let's say its owner is the panel junction snapper. Panel junction snapper is going to catch the get, and it's going to direct the answer of that question off to this method, where we can do some additional work and add our own logic to determine whether or not we should provide a neighbor. Should we provide our junction node as a neighbor? Or in the case of this uh, situation where the node's key is actually our junction node, and so we, as the junction snapper, we actually are going to pass this question off again to our adjacent panel frames, our connected panel frames. And we're going to say, hey, panel, I'm going to pass this junction node off to you. You tell me if you have a, you tell me if you have any neighbors. And so you'll see we call get node neighbors, which is this function. And if our panel frame, which I will navigate to right now, if it also answers the question as it does here, or overrides this property, its get to call this method, same thing, right? We navigate to our node neighbors method, and the panel does have a little bit more robust logic here. But for example, if it's the junction node that's asking for my node neighbors, if I have my power module, remember that first thing we did is we toggled the power module on the panel, right? If I have a power module, I will supply, and if your node is my left junction, if your node's owner is my left junction, I'm going to give you my power module on the left side. If the node owner is the right junction, I'll give my power module node on the right side. So in this way, your connected snappers can actually pass the question off and ask each other whether or not nodes should be provided. And this gives the panel a chance to answer the question itself. So for the junction node, instead of the junction answering for the panel, the junction simply asks its connected panels like, hey, here's my node. Do you have any neighbors that you'd like to give? And in this case, we either provide the power module node on the left or the right, or, and again, this is the beauty of the dynamic system, if we don't have a power module, we provide our pass-through node, which this pass-through node was that gray intermediate node that showed up in the middle center of the panel. If I navigate back to CET, I'll throw a panel in here. The panel is providing this node when we don't have a power module. And this node will be a neighbor of either of these junction nodes. If I were to add this power module, we now have this power module node to the left. It cannot be neighbors with directly neighboring this right junction node, but it can for the left junction node. Its neighbor to the right actually is this node right here. And so there's 4 nodes that are all linked via this neighbor system, but they don't skip over one another. And this one is not a neighbor of this one, not directly. And the left power module node is not a neighbor directly to the right junction node. But through all their neighbors, they're linked. And so this allows for us to dynamically answer the question because this question is going to get asked a lot as the algorithm is ran. Um, and so we get to answer whether or not we should provide a node, given that we know about our pathing node. In addition to this, our pathing node knows about its previous node, which knows about its previous node. So you can get pretty um, funky with the checks that you're doing if you want to go back even a few more nodes to verify whether or not you should provide a node. But that begs the question, how does the animation actually work? I think we need to quickly take a look at that as well. So if I navigate to this pathing directory, you'll notice that there is a pathing node snapper. And this pathing node snapper is designed to be the start end node of an A-star path. Really, it's designed to provide the start or end node of an A-star path. And if we look at the data panel frame, you'll notice that the toggle power module method here that gets triggered by the animation, which we don't have enough time to dive into that specific animation just because we're so focused on pathing. But the key thing to take away from that animation, the toggling of these power modules is actually adding and removing child snappers. So I've toggled this to be on, and there's now a child snapper right on this left side, another child snapper right on the right side, and those child snappers are designed to work specifically with the create jumper animation or the create path animation as it exists at the abstract level. These child snapper nodes, they actually generate their own pathing nodes, and that's why when we have our panel toggled on, we don't generate a pass-through node anymore. We actually ask the child snappers for their nodes. And these child snappers, again, are meant to be the start and the end of paths, and they are meant to connect to a path snapper. So if we do actually create a path, right, we now have two child snappers. One child snapper here, that's a child of this panel to the left. Another child snapper here, that's a child of this panel to the right. And they are both connected to the path snapper. So let's look at this in code. Quickly, you can see how we add our power module children, how we remove them, and sometimes that means we have to break connections. I showed you that earlier. So this is sort of what facilitates the addition or removal of those child snapper, those pathing node snappers that are designed to work specifically with the animations, like I said. But you'll also notice that this pathing node snapper is designed to work with a key, right? So that helps identify this specific pathing node snapper. And actually, the same key for the pathing node snapper will be passed along to the node that is created. And then, of course, the multi-link connector, which I mentioned. This multi-link connector that we've overridden is specifically designed to just ignore a line. And so this multi-link connector ultimately will be connected to two child snapper nodes. So if I were to look at the panel frame here, inspect it, look at its children, it has two children, and if you were to drill deeper, you would find that they are connected to our path snapper. So each pathing node snapper has a key and a path link to connect to the paths that it is a part of. And then if we scroll down, you'll notice that they are designed to generate vessels. These vessels are designed to work specifically with the animations that I mentioned, the animations that we have in place for adding and removing jumpers. And those animations exist at an abstract level for creating and removing paths. So this pathing node snapper is designed to work with those base animations, and the vessels really act as like a proxy to help communicate between the the animation and the snappers, and then to provide some helper graphics as well. I'll scroll down that we've got some stuff with our connectors, our specifically that multi-link connector, but really I want to dive into the pathing while we still have time here. This section here where it actually is supplying its own pathing node with its key and a specific position, which is by default just its to space position. And then of course, the same question, node neighbors. What are your node neighbors? In our case, we've decided now as a kind of a default implementation to just ask the parent. But again, you could override this and do whatever you wanted to do. And ultimately, this system is really extensible. You could override your node classes and provide a different pathing node, maybe not an A-star node, but it's your own node. And you could provide your own algorithm, and you can override the snapper to do a bunch of different things. But this is how it works. And as a general rule, it is designed, these are designed, the pathing node snappers, to ask their parent for nodes, and they're designed to be child snappers. This is where the path is actually created. You'll notice it starts an undo recording, and then it actually splits the path. And this is where that split path logic comes into play, where after a user has clicked on a path, if that path should split up into multiple paths, it'll do that. And it does that by asking for that split bool on the nodes. So given all the nodes in question, should we be splitting paths? And it also factors in that override to figure out whether or not a new path should be created. And in some cases, it's not, like we saw in the case of the two power module nodes when they're adjacent to each other, right? The power module brick connects them. They don't need to have a jumper. Okay, so I'm going to hop over to the Fika Office node snapper here for the power module node, and just highlight how it overrides the pathing node snapper. So one thing it does here is it changes the max number of linked paths that it can be connected to, or it has the ability to do that here. It also is providing its own pathing node, like I mentioned, and it's doing some additional logic here to determine whether or not the previous node is another power module node. And if that's the case, well, we always want to split regardless, but our cost override is actually going to be 0 in that case. So we're going to do something a little bit different. This could probably be written a little differently, but basically it's going to override the cost here and make it 0 or free if we're coming from our adjacent power module node. Right, if we're two power module nodes in a row, I pull this up here, right? If I'm this one, and then the next one is this one, right? Like this distance is free. So if we're the second power module node in a row, that distance is free because the brick itself facilitates that connection. This is where we're actually creating our own path snapper, which I haven't shown you the path snapper class yet, but the path snapper is what's created when a path is created. And it also has that same multi-link connector where it's connected to its nodes. And it actually has a reference to the path that and all of the nodes that are in its path. And so you can do equality checks on the nodes in the path because again, if you remember our equality check for our pathing node was overridden to check the owner, the position, and then that optional key. So the path snapper does store some state in terms of what paths or what nodes it are part of its path. And then in the case of our Fika Office implementation here, our Fika Office Power Module node snappers, when they are told to create a path, when the animation is clicked, right, to create this path here, they are going to create a Fika Office jumper snapper. So it's a subclass of our path snapper. Again, it's designed to work. These two classes are designed to work in tandem with one another. We've now overridden both and customized both. We have a dummy product rule here that basically says we're not allowed to be a path or a jumper that is greater than 160 inches. So this is an example of a product rule. Um, and then there are some things here to make sure that graphics are only shown a in the electrical view mode, as well as some 3D here to actually show that path in the actual 3D space. So if I switch to normal view mode, right, you can't see the path anymore. And obviously it's hidden inside of here, but these are designed to only show in that electrical view mode. I should also say another thing. Um, so you can see here, this is, aside from overriding some functionality in the jumper snapper and in the panel snapper, this is our sort of like electrical package that we have in Fika Office. And these are the classes that we provide. And for example, the create jumper animation, really the main thing it's doing here is it's caching the previous view mode and making sure that it's setting the electrical view mode so that when we start the animation, like so, boom, the electrical view mode is turned on. When I stop the animation, the electrical view mode is turned off and it goes back to that previous view mode, which was normal. Um, so that's what is done on that animation. Same for the remove jumper animation. And again, a huge reason why is because the vessels are facilitating a lot of the logic, as are the snappers, the node snappers. Our power module node snappers are the only node snappers we have implemented now, at least currently. But yeah, the animations don't require much customization unless you want to force a certain view mode. And then there is the power module vessel, which has some overrides, and then the power module toggle animation. So this again is designed to make a get call, and the vessel is going to do most of that work. But yeah, in terms of the specific customizations, our power module vessel here, this is what's in charge of turning on child snappers, turning on or off those child snappers, right? We toggle them, we create the power module node snappers, or we remove them, right? So if we create them, we're creating these guys, and when we remove them, we're removing them and then potentially breaking path connections if these were connected to a path. I should say that with these being the ones that facilitate the start or the end of every path, the animations are designed specifically to work with these. And so if you don't have any of these in generated or living on any of the objects in your drawing, if you don't have any pathing node snappers, none of the functionality is going to work. So it's up to you to decide when you should have these padding node snappers exist. In this case, it made sense to add and remove them with that power module animation. Ultimately, it's up to the system that you're programming or solutioning, and you need to figure out when or where padding node snappers should exist and whether or not it makes sense to toggle them on or off or have them persist in certain situations. But just keep in mind that the state of the system, right, is stored, if I can find it, in these two classes. The jumper snappers that are created when a path has been created, connected to, so the path snapper connected to the pathing node snappers. So this is where you have physical things in the drawing state for components, electrical things that have been created by the user. Anyways, Thank you for listening. I'm going to call it here. We were able to see how the system works at a high level, and we were even able to dive into some of the specific logic and classes, which I think was cool. And hopefully you found this valuable in terms of breaking down the different sort of chaotic elements that make up an electrical system. And I hope that the example in Fika proves to be valuable. If you have any questions, do not hesitate to reach out via my email. And until this officially gets released in the next few months, you can access all the code at private slash gabba slash Fika Electrical, which is in the base repository. And of course, dev support is always there, ready, willing, and able to answer any questions you may have. Thank you.